In this targeted learning brief, we'll learn what cross-validation is used for and the benefits of a particular type called V-fold cross-validation. Suppose we are interested in understanding the association between an outcome Y and a predictor X. As statisticians, we fit models to the data. If we fit a linear model to the data shown here and plot the predictions, we get this red line. But if we fit a more flexible model that relaxes the linearity assumption, like a boosted tree, we get the orange curve. Both seem to fit the data pretty well, and we'd like to know which one better captures the true relationship between X and Y. We can quantify the goodness of fit. For example, we can evaluate the mean squared error, or MSE, which is the mean squared distance between the observed outcome Y and its predicted value for the model, Y hat. Here, the empirical MSE for the nonlinear model is smaller than that of the linear model, suggesting the linear model is worse. However, models are sometimes overfit to data. That means the model parameters are estimated partly in response to random variation or noise in the data, rather than true signal or the true associations. It's almost as if the model memorizes the right answers rather than learning the best functional form of the relationships between the independent and dependent variables. If we had additional data from the same population, then estimating the MSE using those observations would provide a more honest basis for comparison. Imagine that the blue points shown here represent novel data. In this plot, they fall more or less along the orange curve, suggesting that it better captures the true relationship between X and Y. But had the blue points been distributed differently, perhaps like this, we would conclude that the linear model is superior. But we don't have to guess. We can simply evaluate the MSE with respect to the novel blue data points to get what we call the cross-validated MSE. This is a reliable estimate of the true MSE that would be calculated at infinite sample size. Here we see that although the empirical MSE is smaller for the nonlinear model, the cross-validated MSE is smaller for the linear model. This suggests that the nonlinear model overfit the data, and the linear model is in fact superior. So now we've learned that cross-validation is simply training or fitting a model on data and then evaluating its performance on observations that were not used to fit the model. And the cross-validated performance metric is the right thing to use when comparing model performance or choosing the best from a collection of multiple candidate models. Here's some terminology. The training set or training data are the observations used to fit the model or train the machine learning algorithm. The test set or validation set are observations that were not used to fit the model, but will be used to evaluate the loss function to measure performance. Since it's a loss, small values are superior to large values. You want to minimize the loss. The sum of squared residuals is one example loss function, and the negative log likelihood is another. But both these quantities are dependent on sample size. So what we do instead is average over the sample size by calculating the mean loss, and we call that the risk. And we've already seen one example of the risk. The mean squared error is the average of the sum of squared residuals. A valid loss function should be bounded, otherwise behavior can be erratic and extreme outliers can arise. Now we'll talk about a form of cross-validation known as holdout cross-validation. The colored shapes in the rectangle represent characteristics of observations in the dataset. For example, color represents geographic region and shape could represent age category. In holdout cross-validation, the data are split into a training set and a completely separate test set. Analysts are typically aware that training a model requires sufficient sample size, so you often see in the literature a somewhat arbitrary decision to train on 90% of the data and test on the held out 10% of the data. It might look something like this. The observations in the yellow rectangle are held out as the test set. A problem is that even though the model was trained appropriately on the other 90% of the data, the test set itself is not representative. In this case, it doesn't include any blue squares or purple stars. Because we've failed to assess how well the model performs on observations within those strata, we've obtained a biased assessment of performance. An obvious solution is to increase the size of the validation set. We could specify a 50-50 split of the data, training on 50% of the observations and testing on the remaining 50%. Increasing the size of the test set was helpful, but training on only half the sample raises new issues. This approach assesses the performance of a model trained on n over 2 observations, And if our true goal is to assess performance of a model that was trained on N observations, this approach just falls short. If we train on only half the sample, then at best, the model fit will be less precise and noisier than if we train on more data. And at worst, there'll be more of a tendency to overfit the data, which actually worsens performance. These problems are not really an issue when the sample size is in the hundreds of thousands or the millions. But even at seemingly reasonable sample sizes with several hundred observations, holdout cross-validation can still be problematic in high-dimensional data, or when the dependent variable is a rare binary outcome. Another alternative at the other end of the spectrum is leave one out cross-validation. For this scheme, one observation is omitted from the training set at a time. Here we start by holding out the purple square and training on the remaining n-1 observations. Then we evaluate the risk, the MSE, for just the purple square, and now move on to the blue star. Train on all observations except the blue star, and then calculate the MSE with respect to just the blue star. This process continues until every observation in the dataset has been held out once. The cross-validated risk is the mean of the MSE across all n validation sets. In other words, it's averaging over the entire distribution of the data. The virtues of this approach are that each of the n distinct training sets has size n-1, so it's quite representative. And at the same time, the risk is also an average over the entire distribution. The only drawback is that this approach doesn't scale well to large data sets due to computation time and memory constraints. An intermediate approach is what's called V-fold cross-validation. For V-fold cross-validation, the data are divided into multiple training and test sets. For example, we can partition the data into V equals 20 disjoint validation sets. Each set contains 5% of the observations, and each observation is assigned to exactly one set. We can consider each set in turn as a validation set, and as shown here, the observations in set 1 are held out, and training is conducted on the 95% of observations in sets 2 through 20. But we don't only do that once. After we evaluate the MSE using the held out observations in set 1, we move on and hold out the observations in set 2 as the test set. We train on the 95% of data in sets 1 and 3 through 20, and then evaluate with respect to the observations in set 2. We repeat that until we finally have 20 estimates of the MSE. And then our overall estimated cross-validated risk is the average risk estimate over all the 20 validation sets. In this way, each training set faithfully represents the distribution of the data, and the CV risk itself is calculated with respect to the entire data distribution. Unlike leave one out cross-validation, this approach is quite scalable. In fact, at larger sample size, smaller values of V can be appropriate, for example, 3 or 5 or 10. Compared with holdout cross-validation, V-fold cross-validation makes more efficient use of the data, resulting in a narrower confidence interval around the risk estimate. V-fold cross-validation provides an honest assessment of performance that allows us to compare models and select the best one. An important use of this is setting tuning parameters that control the behavior of machine learning algorithms. V-fold cross-validation is the foundation for superlearning, an ensemble machine learning approach that is part of the targeted learning estimation toolkit. We'll talk about superlearning in another targeted learning brief.